All right, so so we're in chapter 4 now, as you guys may remember, and so this will be tested on final exam part 2, but final exam part 1, you'll be focusing on tests 1, 2, and 3, right? It's a comprehensive review of those, and from what I've seen in grading test 3, you still have some work to do. Let's see here. But we'll get back to that when we review. So I'm going to forge ahead here with the log stuff. And I would say roughly we're in section 4.3 at the moment. I've shared with you some of the properties of logs. I don't think we've done change of base yet, though, have we? Have I showed you how to go from one base log to another? I don't think I have. So we should do that. And then I will try to dive into a wide, just start attacking a bunch of examples on how we use logarithms to solve equations, and just how to solve equations involving logs and exponentials, because that's our larger goal in this chapter, is so that, you know, if you're in a science class and you have to solve for an exponential or something, you have a way to do that, you know what you're doing, right? Now, so first of all, the change of base thing. So here's the way it goes. So for one thing, I usually talk about the rule for logarithms, and I'll start with that, I suppose. But log base b of x is equal to log base a of x divided by log base b of a. Wait a minute, other way around. Log base a of b. So this is how we can change from, say, base b to base a. Now, a special case would be to you know, change to the natural log. So you could trade this for another, you know, if you pick log base e, well, this would be natural log of x. Aw, man. Sad. Divided by the natural log of b. So, for example, if I wanted to calculate log base 7 of, you know, 30, I could calculate by taking the natural log of 30 and dividing by the natural log of 7. All right? Now, unfortunately, I stupidly left my calculator in the my bag, so give me a second here. I'll log into. Now, the reason this is important is because, well, a lot of calculators that you have, they don't have like a log base 7 function. Some do, some don't, right? But almost every scientific calculator is going to have a natural log function, and it'll be like this big ln button, right? So you can calculate logs using the natural log. That's a handy thing to know. What'd you get? I saw somebody pressing buttons. 1.75? Roughly speaking, is that like approximate, right? Okay, so here's another one. Suppose we wanted to calculate log base, you know, base 10 of, I don't know, e squared. Then that would be the natural log of e squared divided by the natural log of 10. Now that I can simplify. That's 2 times the natural log of, natural log of e squared is what? This is just 2 again, right? So 2 divided by the natural log of 10, whatever that is. I get 0.869 approximately. Okay, so change of base formula it's useful to know about. It can allow us to. It's a good tool to have in our toolbox. Let's just say that. Now, this is how we change base for logarithms. There's also a similar kind of trick we can do. If you want to trade, say, we could trade this. Check this out. So here's a fun fact, if you like. A to whatever, a to the x, we can trade for e to the natural log of a to the x, right? Because e to the natural log of whatever, e to the natural log of something positive is that positive thing again. So this is just an identity, right? But it's useful because then by the properties of logarithms, that's e to the x times the natural log of a. All right? So, for example, radioactive decay with constant k has the number of particles at time t, n of t, equal to the number of particles at time 0 times the exponential of minus k times the time. By the way, this is another notation for exponential which is useful if you want to make like the font of the argument for the exponential bigger so like your reader can see it easier, you know. I oftentimes use this exponential of that. That's understood to be the base e. So like this is a shorthand for n sub 0 e to the minus kt. All right? But as you can see, like this is harder. It's harder to read the exponent when you use the subscript, the superscript notation, right? So this like x of stuff is a useful notation. Say what? It's just another notation, like definition. exp of x is equal to e to the x. At least in this class. There are mathematicians who make a formal distinction between these two things specific to their context, but that will not be us. These will be identical for us. But, okay, so great. That's my point is that there's this formula we know from science, right? If you study particles that are unstable and they decay by the weak force, then there's some decay constant k, and this is this is the number of particles at time t is proportional to the initial number of particles times e to the minus kt, right? So like, if you've got plutonium or something, right? It's not, if you have a kilogram of it, after some number of years, you're going to have less of it, right? Because it decays into other kinds of matter, right? If you had a kilogram of neutrons, if you could have free neutrons, right? The half-life of a free neutron is like 11 minutes or something. So if you could somehow have a kilogram of just neutrons sitting there after 11 minutes, you'd only have like a half a kilogram, something like that. What I just said was half-life, right? So half-life and decay rate, these are different things. What's the half-life? How is that? What's that mean? What would a formula be for half-life? Yeah, half-life formula, you said divide by 2. Something like n of t is equal to 1/2 to the t divided by the half-life, right? That would be the formula for half-life, although I have to multiply that by n sub 0, right? Think about how that formula works, right? If we calculate n of t 1/2, what happens? They cancel, we get 1, so we get 1/2 of the initial amount, right? So if you went to twice the half-life, you'd only have 1/4 of what you had, right? So that's how that formula works, right? So then a natural question to ask is, how are these two formulas related? Right? This is one of those places where you guys have a stupidly large advantage over the other section. If you watch how I did this in the other section, it's so much worse. And I can't. Oh, just the way I came around this discussion was much worse in the other section. I'll just say that. Yeah, I mean, I think I saw this in like chemistry and other places too, right? Like, talk about exponential decay a few different classes, I think. But yeah, it's physics. Okay, so look, basically we're asking, can we solve this equation, right? N0, we're not exactly solving the equation. We're trying to compare two formulas and see if we can understand the relation between the parameters involved, right? Like, it's a little bit more sophisticated than, let's say, solving an equation, right? So really the question I'm asking is, how are K and the half-life related, right? Because initially, I mean, the first thing you notice is that the n sub 0 you can just cancel out, right? That's not part of the story. So we're trying to understand, how does e to the minus kt relate to 1/2 times t over t to the 1/2, right? So I'm getting tired of writing 1/2. The first thing I'm going to do is I'm going to rewrite that as 2 to the minus t over t 1/2, right? I can do that, right? 1/2 is 2 to the minus 1, so that's a property of exponentials. And then I suggest we use that trick I just introduced over here with a equal to 2. Right? We can convert this to an exponential by just saying, aha, well, this is e to the natural log of minus t divided by t 1/2, right? I'll do it. So we have e to the minus kt equal to, you know, e to the where did my 2 go? I'm sorry, it's garbage. Sorry, my mind skipped. That was e to the natural log of 2 to the minus t over t 1/2, right? That's the trick. But then we can pull out the minus t over t 1/2 and multiply by the natural log of 2 by the power property of logs, right? So one of the things I keep using is this, the natural log of stuff to a power is equal to power times the natural log of stuff. So like that's one of our properties of logarithms that we're going to use again and again. We can pull powers out. And then once I've got e to the something equals e to the something else, what can I do? What's the natural enemy of the exponential? What should we do to this equation? How about we take the natural log of both sides, right? What happens if we take the natural log of both sides of this? Remember, natural log of e to the whatever is whatever. It's whatever's there. So the e and the natural log and the e cancel out in the sense of function composition. And I've got minus kt equals to minus t over t1/2 times the natural log of 2. At this point, we can cancel the t's, right? Because this identity holds for all time, so just divide by time. And what do you got? And get rid of the minus 2, right? So we got k is equal to the natural log of 2 divided by the half-life. And that is the relation between the half-life and the decay rate. So maybe you'll take a class in chemistry or something where you need to convert between half-life and decay rate. This is the pre-calculus, which explains why those are connected. For example, if I say, okay, so the decay rate is 10, what's the half-life? You could figure it out, right? If I solve this for half-life, what do I get? Right? So if k was 10, what would be the half-life? Natural log of 2 divided by 10, which is about 0.069. .069 watts, Well, that depends on the problem statement, right? If you're given a decay rate, it has to be in terms of some unit of time. It might be in terms of years, might be in terms of seconds. It depends, right? Now, the same math works for population growth. What's the difference with population growth? What's the formula look like for population growth? What's the difference? The big difference is that it's not a decay rate, it's a growth rate, right? So you just get rid of the minus if you want to keep k positive, right? So like population growth is something like p0 e to the kt. That's exponential population growth. And you can talk about the doubling time for the population. The doubling time will also be, well, I guess we have to talk about doubling time. But I think everything pretty much goes through the same, except without the minus. And without that minus there, well, I guess I should work at, hey, that sounds like a good homework problem. That would be one of your homeworks. So I will go through a similar investigation for the doubling time for population growth. That would be one of your homeworks. It will homework problem. It will mirror this discussion. So, all right, now, let's start attacking some problems. So, first of all, let me remind you our major rules. What are they? In terms of the natural log notation, like natural log of xy is natural log of x plus the natural log of y, right? The natural log of x over y is natural log of x minus the natural log of y. And of course, the other one I just mentioned, natural log of x to the power p is p times the natural log of x. So these are like, pretty important simplifying rules for logarithms, right? And then we have other stuff, right? Like the natural log of e to the x is equal to x. That's another nice one to know about. What else do we know? Like natural log of e is just what? It's really just a special case of the formula right above it, right? Like x equals to 1, right? Natural log of e to the 1 is 1 again. So, and of course also natural log of 1, well, that's natural log of e to the 0, which again is 0. So if you understand the top one, you can get these for free, but honestly, I think it's good to have these memorized, all right? At least they should be on the sheet of remembrance, right? Now, what do these rules look like the other, like we could also talk about log base. All of these rules could be replaced by log base A, right? So log base A of x plus log base A of y, and et cetera, right? So like log base A of a to the x is equal to x again. Right? So all of the rules I was just stating for base E also can be stated for base A. Right? Okay. Now, I solved this equation that I'm currently erasing by taking the natural log of both sides, right? But there's an important theorem we should also know about. One-to-one property of exponentials and logs, right? So here it is. If you have a to the power x equals to a to the power y, that implies x equals to y. This is the one-to-one property for the exponential. So the proof of that is just to take the natural log of the equation and divide by the natural log of a. And I mean, proof is very, here's the proof. Natural log of a to the, well, forget natural log, let's take log base a. Log base a of a to the x equal to log base a of a to the y. What happens? That implies x equals to y. So the proof is very short. Essentially, by the definition of a logarithm, this is true, right? This is also true for logs. If I have log base a of x equals to the log base a of y, that implies x equals to y, right? What's the proof of that? I don't do many proofs in here, but here I think it's warranted. I just take a to both sides, a to the log base a of x equals a to the log base a of y, but that tells me, again, x equals to y because the log and the exponential are inverse functions. Now, there is some fine print, right, that I'm currently suppressing in this theorem. Let me call this one number 1. Let me call this one number 2. So what's the fine print for number 1? Is there any fine print for number 1? Are there any strings, conditions that we must place on x and y for this implication to be reasonable? The answer is no. The domain of a to the whatever, the domain of the exponential function is all reals. But in contrast, part 2, that's only reasonable if we know what? I mean, we need to know that whatever we're plugging into the logarithm is actually what? It needs to be positive, right? So this, technically speaking, this is given x and y greater than 0. All right. Just to be picky, I mean, this can be an issue. So that's very nice because if we're trying to solve an equation involving logarithms, if we can get log of something equals to log of something else and they have the same base, then we can just equate the inputs to the logarithms, just like that. But it has to be a single pair of logs, one on each side. No extra signs, like if there's a minus outside the log, this is not true. And it has to be the same base. If they have different bases, then we can't just equate them. It's not the case, all right? So let's work some examples. I'll start out with some easy examples. If I have 2 to the x equals 8 to the 3x, you're like, well, it's not as easy as it could possibly be. That's true. But can you convert 8 to the 3x to a 2 to the x? That's 2 cubed, right? to the 3x. So what do I actually have here? 2 to the what? 2 to the 9x. So by part 1 of this theorem with a equals to 2, this implies what? X equals to 9x. If x is equal to 9x, what's that tell you about x? I mean, this tells me that 8x is equal to 0, which of course tells me that x is equal to 0. So the solution is 0. Can anybody, so you're like, what if I didn't see 8 was 2 cubed, right? Or what if we change this problem ever so slightly? Instead of having 2 to the x, you have 7 to the 3x. What do you do then? Right? It's easy to throw a monkey wrench in the plans here, so to speak. What if instead of solving 2 to the x, you've got 7 to, let's say, 3 to the 3x? See, I don't know. There's no nice way to convert 7 to 2 to the power, right? So when I see something like this, what I do is I just take the natural log of it, because that's a way to change it from an exponential equation to a log equation. So if we take the natural log of this, what do we get? This is x log 2, right? 3x log 7 by the power property of logs, right? So this gives me x times the natural log of 2 minus 3 times the natural log of 7 equals to 0. It's out there. And, well, I invite you to check it out, but this right here is not equal to 0, right? Actually, could you guys tell me how to simplify that into a single natural log? What I've just underbraced in orange, can you write that as a single natural log? How would you do it? There'd definitely be a good part of your homework about simplifying expressions using logarithms, right? So I've kind of jumped the gun and not done many examples about that. I've just sort of forged ahead to solving equations because I think that's the most interesting part, right? But we do need to gain this skill of simplifying logarithms. This is an example of that. Like, how can you combine these two into a single log? I'll get us started. This is the natural log of 2 minus the natural log of 7 to the power 3. And then I can write that as the natural log of the quotient of 2 by 7 to the 3rd power. So when is the natural log 0? Let's see right here. Natural log of 1 is 0. The natural log is a 1-to-1 function. That means that the only thing that gives you 0 when you plug it into the natural log is 1. So if the input to the natural log is not 1, it means that the output's non-zero. In other words, is 2 over 7 cubed 1? Nope. So even without getting a calculator out, I can tell you that this natural log is non-zero. And therefore, I've got x times a non-zero number, which tells me x is what? X equals 0, right? So it looks like all my examples have solution 0. See if we can do better. Let's see if this textbook's got anything nice to chew on here. This one's kind of nice. This is number 26 from section 4.5. All right, so here we're asked to solve 5 to the minus x over 100 equal to 2. All right, so this one, did you already pan over here? Okay, cool. So what do you guys want to do? What do you think we should do here? Do the ln. I'll allow it. Let's see here. So natural log of 5 to the minus x over 100 equals to the natural log of 2. Well, natural log of 2, we're pretty much done there. And this one, we can pull out the power, right? So we have minus x over 100 times the natural log of 5 equals to the natural log of 2. Solve for x. X is 100 natural log of 2 divided by minus the natural log of 5. There you go. And of course, we could plug it into the calculator and find a decimal if we wanted to. But in this kind of, in this course, like this is a totally legit final answer in my book. Like you don't actually have to plug it into your calculator and find a decimal. In this sort of problem, I would be content with this as a final answer. Unless, of course, I add the instructions, please find a decimal answer. Which, of course, would just be laziness on my part, right? Because it's much easier to grade decimal answers as opposed to this. Although I don't know, I guess I can't imagine another way you might change the answer there much. Let's work another. Let's see here. Here's number 28, same section. 2 times 5 plus 3 to the x plus 1 equals to 100. So divide by 2, I like that. Divide by 2 gives me 5 plus 3 to the x plus 1 equals to 50. Minus 5. Now, why didn't you take the natural log already? Because we're trying to simplify what? Exactly. We were trying to isolate the 3x plus 1. Because we have no nice rule. Nowhere have I written natural log of a plus b equals anything nice. This is false. There's no such rule. Like natural log of a sum, nothing happens. So we have to isolate 3 to the x plus 1. So that's 45. Now ln, now take the ln. Take out the x plus 1. Yep, that is how you do that. So if we can isolate the exponential, then we're good. We can we can do problems like this. Now, not all the problems are like that. There are other things that go on. But these 4 examples we've just done, that's oftentimes what you need to do, is something like these 4 examples we've already seen. He also has some examples here that are kind of sneaky. E to the 2x minus, I mean, this is kind of the next level. This is a more sophisticated example in terms of the trickery going on here. This is number 39. And there are other examples, like we might want to solve something like, you know, log base 2 of x plus log base 2 of x minus 3 equals to 2. We'll talk more about these kind of things. We'll do much more of these kind of examples next week. 3. There's a 3. So this one, the trick here is to make a substitution. So let y equal e to the x, then y squared is e to the x squared is e to the 2x. And so this equation up here is actually quadratic in y. That's y squared minus 3y plus 2. So you go, oh, I know how to factor that. Right? And so either y equals 1 or y equals to 2, right? But what's y equal to? We said e to the x, right? So then I take the natural log of that. I get the natural log of 1 equals to x. The natural log of 2 equals to x. So this one, what's natural log of 1? I can simplify that. That's x equals to 0. Or natural log of 2 is x. Those are both solutions to this quadratic. How about this one? What do we do here? How do we solve that one? Well, this one, we use the property that the log of a sum is the sum of logs is the log of the product. So log of base 2 of x times x minus 3 equals to 2. Now, you can either convert that 2 to like log base 2 of something, right? What would 2 be log base 2 of what? Maybe that's a good exercise, actually. Log base 2 of what is 2? Remember, we have an identity. X equals log base 2 of 2 to the x, right? So we can use that identity to see what we should put there. It should be 2 to the 2. So there's a 4. A 4 goes here. Just using this identity over here. But then by the one-to-one property of the log base 2, right, we get what? We get that this is equal to that. So we get x times x minus 3 equals to 4, which is x squared minus 3x minus 4 equals to 0. And what does that give me? X minus 4 times what? X plus 1. So that gives me 2 solutions, right? X equals to 4 and x equals to minus 1. Game over, right? Wrong. Game not over. Remember, there's a string attached. When you apply this to this, what's the string? What do we need? It requires x and x minus 3 to be positive. If that's not true, we're in trouble. So the name of the game here is after you use the property of log and you find the corresponding whatever, solve it, you got to go back and check the original problem again. So what's happening here is that the solution minus 1 is extraneous. This is extraneous. It's not even in the solution set. You can try plugging that back in. You get log base 2 of minus 1. Es no bueno. Not allowed. So x equals to 4 is the solution here, just that one. In contrast, up here, they're both fine. So is there one solution? Is there two solutions? Is there no solutions? It just depends, right? So anyway, I'll stop there for today. And I'll try to get you guys your homework to start chewing on sometime soon. But again, one of my major goals next week is just to review